So today we will learn some new concept. Okay, it's the major concept we will discuss is clustering. Is it clustering? Yeah, it's about clustering. Okay, and previously we learned quite a number of machine learning algorithms, and we said they are supervised learning. Is it so? You have a data set, and that data set provide you with features. Is it? And we also have target. Is it? That's generally speaking, it's X, Y as the values. And then sometimes we do a classification, sometimes we do regression, is it? And those are called supervised learning. So they are under supervised learning. And for unsupervised learning is, it's kind of, you don't have a target, is it? But the goal is you're going to find some nature grouping in the data so that you can group a certain number of items together. Okay, so this kind of concept, we call it cluster. Okay, cluster. Okay, so for cluster, today what we are going to learn is we're going to learn 3 new concepts. The first is k-means algorithm about clustering. The second is hierarchical clustering. Okay, and it involves, we will see, a tree kind of structure. And the third one we will discuss is called the density-based clustering approach. So let's move on, okay. And over here, we also explained it's the clustering, it's regarding what we call it's prototype-based clustering, okay. So the idea is that each cluster is represented by a prototype. Okay, the prototype, what is that? Is that can be either the centroid of some similar points. Okay, later on we are going to see. Or it's, we call it medoid. Okay, the medoid concept is most representative of frequently occurring point. So those we call it prototype-based clustering. And the 3 ones that we just discussed, it's under this prototype-based clustering. So first, let's take a look. What does it mean? The first one, the k-means algorithm. Okay, k-means. And don't get this confused with KNN. KNN is k nearest neighbor. Okay, this is different. That's supervised. And this is k-means. So what that is? K-means, the first is identify its feature as k-means it's good at identify cluster with spherical shape. So be careful about this, and why it is later on we will see, okay. And the drawback is, because it's called k-means, is it? So before you know, and you kind of need to know beforehand, like how many cluster you want it to have. So that's a drawback. But basically, over here, we set the clustering, so that means you don't know, is that you have no idea how many cluster. But here, the prerequisite is you need to know the cluster. So basically, over here, we'll see it's going to trial, is it? So how k-mean algorithm works? So let's see. So the basic idea is you define how many cluster you want. You can also try. Later on, we will see in our examples, okay? And then after you define the number k, is it? Because here it's, we said it's kind of sphere prototype, is it? So after you pick the number k, then you can select in your samples that k centroid. So random selection kind of. You just pick some k random points, and then you assign them as centroids. Okay, what we call it center kind of. Okay, and then you assign other samples to the nearest centroid that you just assigned. Okay, and then you can move the centroid to the center of the samples that is assigned. But this is just the initial assignment, is it, that won't be precise, is it? So that's why for k-means, you need to repeatedly, so within the loop, you need to repeatedly repeat assign sample to nearest centroid, and you're also going to update the centroid. So the centroid won't be like once it's assigned, it's never going to change. It's also going to dynamic adjust to change. So you keep repeating the above two steps until what? Until your class assignments do not change, or you define some user-defined tolerance, or some maximum number of iterations reached. Then you can stop this k-means algorithm. And the k-means, because you are going to assign off the other samples to the centroid, and the rule you based is based on the closest. So we define on the closest. Is it the closest? Then how do you define? It involves the distance calculation. Is it? So generally speaking, here it says you can use Euclidean distance for the your definition of the k-means closest distance definition. Okay, use a squared Euclidean distance between 2 points. And be careful, this 2 points in m dimension. Okay, depends on how many features the data set has. It's not a 2-dimensional. Okay, so be careful here. So x and y both are just some vectors. Okay, it's m dimensional. So here it's Euclidean, square Euclidean distance is defined like this. And it says based on this Euclidean distance matrix, is that we can describe basically k-means algorithm. It's just some optimization problem. And the optimization is based on what criteria is you try to minimize what? Within cluster, the sum of square of errors, SSE, So this is your centroid, centroid, okay? And this is the samples that within your cluster. So you have the clusters, you have the centroid defined, and all of the other samples, this is the distance. So you're going to keep trying to optimize this, minimize this, So that's the goal for k-means. Okay, and the k-means, here it says there is an issue with k-means, because you need to run multiple times on the data set and then choose the best performance. And sometimes over here, if you random seed, they place the initial centroid, sometimes it can result in a bad cluster, some bad clustering, or it's very slow to converge, okay? So there are some drawbacks here. So there is an improvement. Here it says, we call it k-means plus plus, okay, k-means plus plus. So k-mean plus plus, the key point for the initial centroid is not a random choose. Okay, so suppose you have some cluster of data, So the centroid, you're going to pick the 2 furthest away. So this is mu1 and this is mu2. You're going to pick the 2 farthest away samples. Okay, those 2 samples as your centroid. So in this case, then it can improve, okay? So that's the k-means plus plus concept. So you're going to pick the 2 furthest away points. samples as centroids. That's just initial centroid, okay? And the above we discussed clustering is called hard clustering. That's a hard clustering because you're going to assign the sample, okay, in exactly just one cluster. So that's k-means. And a lot of time you can do some flexibility, okay? So do some flexibility for the clustering assignment is we call it soft clustering. So soft clustering, another concept is called fuzzy clustering. Okay, so fuzzy logic concept, is it? So fuzzy logic is concept is you are not going to just 0 or 1, is it? When you do assignment, either 0, 1, either white or black, is it? It's a fuzzy. Fuzzy, what's the concept is you're going to replace that with the probability of the sample belong to certain cluster. Okay, not 100%, is it? Because hard one means either yes or no, is it? But with fuzzy, the fuzzy concept is maybe, okay, 75% yes, is it? And another 25% may be no. Okay, it's not 100% yes or no, okay? So this concept, we call it soft clustering. So it make use of a fuzzy logic concept, okay? So it's we call it fuzzy C-means, okay, fuzzy C-means algorithm, so FCM. So that's the concept of a hard versus soft clustering. So we are going to just get to the concept. And then the next idea is about, like we just discussed, is it about k-means? K-means the most important element to impact your performance is this number k. Is it how can we know the best number of clusters? Is it? So there is a way we call it an arable method to find the optimal number of cluster, find the k. Okay, the arable method basically is you just try different number of k. Is it? So you trial, is it, with different number of the k values, is it? And then you can find what give you the best estimate, is it? So later on in our example, you will see we can have some plotting that can clearly reflect how you find the optimal number of the k, is it? And over here it says, because of what? There is a definition called distortion. Okay, distortion basically is just our within cluster, the sum of square of error. Okay, and that distortion, that's SSE, can be accessed with what? When we learn the sklearn, okay, the library, there is a parameter that you can access. It's called inertial. Okay, so through this inertial, then you can get to the distortion. And with the distortion, that's basically if you increase k, the distortion will decrease. Okay, then based on this feature, then we will see you can find the optimal number of the k. So that method we call it arable method. And there are some other ways that we can also quantify the quality of clustering. And over here is another kind of plotting. We call it a silhouette plot. Okay, silhouette. You will see in our example, it's quite interesting. Okay, so silhouette plotting. And silhouette, there is some coefficient. We call it a silhouette coefficient. And generally speaking, silhouette coefficient is bounded in the range of between -1 to 1. Okay, and what's the optimal silhouette value? So if the silhouette coefficient, the value close to 1, then that means your clustering is quite good. Okay, so that's the silhouette concept. And then previously we discussed it's called k-means, is it? So the key concept for k-means is you can select some centroid, is it? Some centroid, and then all of your samples, is it based on the centroid, you find the closest distance, then you assign the samples around this centroid, is it? And then you can keep adjusting, okay? And a lot of time you may also merge the different clusters, is it? So that's called k-means, so based on centroid. And over here, we discuss the second clustering approach. It's called a hierarchical clustering. Okay, hierarchical clustering. So for hierarchical clustering, so it also involves some plotting, and we will see in our example. Okay, so we can plot what a plot we call it a dendrogram. Okay, the dendrogram is kind of just some binary hierarchical clustering. Okay, it's some kind of like a tree-like, is it? And that will help us interpretation of the clusters. Okay, the cluster. So that's why it looks like something like this. Okay, so you have, and then you can keep doing like this. Okay, so that's called so this kind of drawing, okay, you call it a dendrogram. Okay, so that's, and visually you can also see is it's a hierarchical, okay, clustering. And in this case, then if you set like the threshold here, you will say, oh, I will just have two clusters. Is it all of the samples fall under this tree belongs to cluster 1, and all of the samples fall within the right cluster, then it's cluster 2. So that's the concept. And under hierarchical, we have a main approach, agglomerative, hierarchical, or divisive, okay? And it's opposite of each other. So divisive hierarchical clustering says start with a single cluster. So you have all of your samples included as a single cluster. Then you keep splitting them into smaller cluster. Okay, so that's the concept of divisive. And versus divisive, we call it agglomerative. So the dendrogram way I draw here, it's reflect the agglomerative clustering. Agglomerative is start with each sample as individual cluster. So each sample is considered as a single cluster. And then you merge the cluster close together, and until you only see a single one. Okay, and then depends on where you want to cut, is it? And then you can find how many clusters will be the optimum. So this is the general concept about hierarchical clustering. And for hierarchical clustering, then the concept is how do you do the merge? Is it how do you pick the merge? So here there is a concept, a term called linkage concept. Okay, and linkage concept. And this can be used to describe. So we are going to define some distance, is it? So the cluster distance definition. Okay, so with this linkage, there are two listed here. Okay, for the agglomerative. But later on we will see there are more options. The first definition called single linkage. So what's the concept of single linkage? Single linkage is to pick, so over here, because it's agglomerative, is it agglomerative? You're going to merge two clusters together, is it? To one cluster. So that's your goal, is it? Because you merge, then there are multiple options. How do you choose two clusters that you're going to merge, is it? So the first concept is called you choose a single linkage. Single linkage, so single link, the definition is distance between two closest elements in cluster. So in this diagram, we have this red group and the yellow group. Is it between these two groups, the two closest samples? Those are two closest samples from two different clusters, is it? And those two, the closest. So you choose those as the distance to do the merge. Okay, so you compare, suppose this is the blue cluster, is it? You have data. And the blue cluster, then the distance between red and the blue, if you compare, okay, this, suppose we call it D2. Here is D1, is it? Then D2 greater than D1, is it? So that's why I'm not going to merge with the blue one. I'm going to merge with the yellow one. So that's the idea. Then you have both of this together as a single cluster. So that's the concept of single linkage. Okay, and with single, if you choose single linkage, then what's easy to produce, your cluster will look like a more long chain together. Okay, especially if you have some data that look like this, then you have cluster, is it? And then that's going to be lead to linked together as one cluster. So it's easy to produce a long chained kind of cluster. The second type of the linkage, the cluster distance, we call it complete linkage. Okay, so what's this concept? Complete linkage choose the distance between two furthest elements in clusters. Two furthest, okay. So in this case, the two furthest is between the yellow and the red, is it? Yellow, and then among different clusters, is it? Among the different clusters, so the closest, the furthest, is it? Suppose, okay, here is called D2, and here is D1, is it? Assuming over here I have another blue color, okay. So let's rewrite, because then that's. So anyway, these are the two furthest distance, is it? And suppose I have another blue one, okay. So this is also blue color, okay, blue dot. Then the furthest between the blue, so this is D1, and between blue and the red is D2, is it? And between red and yellow is D3, is it? So the furthest, okay, among all of the your samples within your cluster, is it? So you have this cluster, you have this cluster, and you have the yellow cluster, is it? The furthest distance. Then in this case, obviously you can see D1 is the smallest, is it? That's why when you choose the merge, you merge these two together, is it? So that's called a complete link, okay? And the complete link, then it's easy to, the cluster shape will look more like a what? Will look more like a sphere, okay, sphere kind. So that's a concept of single link and complete link. And here to give us a visual result, is it, between these two. And if you take a look, you will see, that you will see, if you use single linkage, is it the different color? Is it? It's more chain-ish, is it? But if you choose the complete linkage, then you will have this count as one cluster. This will count as one cluster, is it? So these two results completely different, is it? So when you choose how do you do the agglomerative, so the linkage concept is also important, okay, which you choose, is it? So it will give you different result, the clustering result, is it? And sometimes some shape just naturally prone to certain distance you choose, is it? So we need to be careful when we do the agglomerative clustering, okay? And over here, it explains more concept about the distance. So previous we explained this too, as we already know. And there are some other distance. And the third one is called average link. Okay, average link, the concept is average all of the pairwise distance. Is it? And then its advantage is less affected by outlier. So it depends on also liar, because in this case, we'll consider all. And among all of them, it will choose the least and then do the merge, is it? And of course, because you consider all within the cluster, so that's why it will be less affected by the outliers, okay? The third one, the next one, what it choose the centroids. Is it? Centroids, then the distance between centroid of the cluster, like this diagram shows, is it? So you choose the centroid. And suppose you have another centroid. And then among that, you just based on the distance. Is it? So in this case, this is D1, D2, D3. That's close. We can say, oh, this is too close together. Is it? So that's why you can group these two together. Okay. So that's called centroid. And the other one is called Watts method. Okay. Watts method is consider join two clusters. How does it change the total distance from the centroids? So you will pick, so this is going to be a new centroid if you merge them together. Is it the total distance? Versus like over here that, okay, I have the cluster, is it, then I add them together. Is it how it affects? Is it? So this over here, what the concept shows us, just you can pick different ways, okay? Because later on in our example, you will say, oh, sometimes the parameter plug in with single or complete. What does that mean? So now we have some idea. And over here, it also gives us another concept. It's called Lance-Williams algorithm. Basically, this algorithm, it has a single formula. Okay, this is a single formula, but it considered all sorts of the ways of the distance you can calculate. So you can also not just choose a single, like I just choose the complete or the single. Is it? I wanted to choose multiple ways for my distance calculation. So this kind of more hybrid or combined, is it? That's also allowed, okay? Then in this case, like over here, then there are some coefficient. Okay, so the weights. So if you choose like a single linkage, is it how the alpha 1, the alpha j, or alpha I, alpha j, or beta, or gamma? So what are the weights they will play? Is it in this distance calculation? Okay, so this is the concept about Lance-Williams, just more combined. Okay. And then over here, let's see the idea about the linkage and the hierarchical clustering uses the dendron diagram. Okay, so here we show, so here is your data set. The data set just a student's grade. Suppose these are student grade and versus a student ID. That's our data set, is it? And if you want to do the hierarchical clustering, you see over here we do bottom up. So basically it's agglomerate, okay? So over here, you first need to generate this matrix. We call it approximated matrix, is it? And over here, a list of the samples, is it? List of the samples, and then for each of those are the distance between those two samples, is it? So let's see. Okay, this is student 1, is it? So student 1 to student 1, of course, the distance is 0, is it? But student 1 versus student 2, the distance is what? The difference between this is 3. That's why you have 3, is it? Then let's see, 1 to 3. 1 to 3, is it? 1 has mark of 10. 3 has mark of 28, is it? So the difference between 28 and 10 is 18, is it? So that's how you come up with this 18, is it? And then let's see, 4 to 1, is it? And the 4 to 1 is 4 is marked as 10 or 40, And 1 is 10, is it? 20 minus 10, that's how you come up with this 10, is it? And the next one is 5 to 1. Is it? 5 to 1 is 35 minus 10. That's how you come up with 25. So with this data set, then you can come up with this approximate matrix, is it? Once you have the proxy matrix, then like previously we explained, is it? Because all of this represent what? Represents the distance, is it, between any two samples, is it? So then you check, okay, of course, the distance between 1 and 2 is the closest, is it? That's why you're going to group these two together, is it? Group these two together. Okay, so, and once you group that together, then basically you kind of take 1, 2 off, is it? And you have this new, so that data set is going to be substituted with this, is it? 1 and 2, is it? And 1, 2, how you choose the mark? You choose the largest one among that, is it? So now you have this data set looks like this. Then you need to get to the approximate matrix again, is it? So we are going to repeat like that to find all of the distance again, is it? And then you have the distance matrix, you will find the smallest is going to be 7. Is it? 7 is between what? It's between node 3 and node 5, is it? So that's how you come up with, you're going to group 3 and 5 in a cluster, is it? 1 and 2 in a cluster, is it? And after that, then you can continue do the same thing, is it? You have this new data set formulated, is it? And now you will only have 3 rows, is it? Because you group 3 and 5 together, is it? And then you choose the distance, is it? And so it's not going to be, it's going to be 35, is it? You're not going to have this, is it? And then you recalculate this approximated matrix, is it? And then you will find, oh, the next cluster is I can group 4, 2, 1, and 2 cluster, is it? So these 3 will be in 1 cluster, is it? And then last, you can group all of them together in 1 cluster, is it? So you can use this to draw the dendrogram, because over here it also shows the distance. Based on your approximate matrix, is it also gives you distance, is it? So that completely shows the distance. So this is 3, this is 7, is it? And next is going to be 10, is it? The distance from this approximate matrix, is it? And then what you can do is, oh, you can choose some threshold. You said, I want to choose some threshold, is it? And I'm going to use that threshold to see how many clusters I can get, is it? So in this case, I said, okay, I'm going to choose the distance of 12 as the threshold. Then I cut it, is it? Then in this case, it's clearly show you're going to have 2 clusters. Okay, so that's why we call it hierarchical, is it, using dendrogram. So then it will clearly give you the clusters and the samples belongs to which cluster. So that's the concept of the cluster, hierarchical cluster, okay, using dendron. The next one, we call it, the third one today, we will say it's called, it's going to use density. So it's a different concept compared with the other 2, okay, density. And the method, we call it depth scan. Okay, this depth scan, the complete name is density-based spatial clustering of application with noise. Okay, it's also considered noise. Okay, so what is the concept here is there are 2 parameters here we need to consider. One is minimum number of points in a cluster. So you need to define this parameter. The second one is this radius. Is it the radius? And so once you know the minimum number of the points, is it? And we can also label all of the samples as three kind of point, okay? Core point, or border point, or noise point. So what's the definition of core point? Core point is, okay, if a point, okay, within this radius, so you kind of draw a circle, is it? And then you can count how many points fall in this circle. And if it meets the definition of your minimum number of points, then this point will be defined as core point. So you can choose any one. Is it like, suppose I choose this one, and then I draw the circle, is it? And you can find, you can see there is only probably 1 point fall within the circle, is it? So of course, this doesn't meet the minimum 3 definition. So that's why this point you can only define as border point. Okay, border point. And what's the noise point? Noise point is you define the circle, there is no point to fall within it besides this cell, is it? So then that point is called a noise point. Then based on what we just explained, then you can clearly see, is it? This is based on density, is it? Because you have certain area, and then you will count how many points fall within that area, is it? So it's purely based on the density. And of course, if the data more located close together, then you will clearly have some cluster, is it? So that's the concept of density based, okay? And so that's the concept of 3 clustering algorithm. And then over here, it says, how do we choose the clustering algorithm, etc. And it depends here, it says algorithm, and also it's a hyperparameter, okay, hyperparameter. And also previous, we also say the distance matrix also plays very important role, is it? And a lot of time, of course, your domain knowledge, is it? And a lot of time, we can also apply dimension reduction. Is it like previously we learned the PCA? Is it LDA? Is it those dimensionality reduction technique? Is it? And then you can do the clustering after that. And you can also compress your data. Is it? After you compress data to 2 dimensions, then it helps easy to do some plotting, then it will also be easy to do clustering. Okay, so that's all the conceptual idea. Okay, and next let's take a look at an example. Okay, in sklearn, how do we do the clustering unsupervised? Okay, so the first example here, let's see. So over here, we just random generate some number. Okay, in sklearn, there's a data set called make a block. Okay, you can random generate number. Over here, we are going to have 150 data sets. Okay, and we only have 2 features for this data set, and we choose 3 centers to generate the blob of data. Okay, and then over here I also have the data what it look like. Okay, the y and x value. So over here basically we have 3 target, 0, 1, 2, etc. And then you have the x value. Okay, so that's the data part. Okay, and then next, oh, this is not, let's, okay, so over here, let's see what does the data just look like. And previously we learned plotting, is it the matplotlib pilot. Okay, previously we explained. So over here, a lot of time, you can, the very first thing you can do is you can draw your data, is it? Can draw your samples. In this case, we just draw scatter because you only have two-dimensional data, so it's easy to visualize. Like the previous discussion, we said you can, a lot of time if you want to visualization, you can also apply dimension reduction, is it dimensionality reduction? You can compress the data into two-dimensional, then you can also do this kind of drawing, so that it help you to identify the cluster, is it? And this is just some scattered drawing, is it pretty simple? And you also apply grade, is it? And from this drawing, plotting, we can clearly see there are three clusters, is it? Three clusters. Okay, then next, let's see, how do we do the k-means, is it? So over here, we are going to import the k-means. And the k-mean, you see over here, you need to specify the cluster, is it a cluster? And the initial placement, how do you place? Here it's random, okay? We didn't apply the k-means plus, okay? And you also set up maximum number of iteration, is it? And the tolerance, is it? How do you, so both of this used for how you make your learning algorithm to converge, okay? So this is for convergency, is it your algorithm, okay? And then after you apply the k-mean, is it, then we can apply our, the data that we just generated, is it, to do the model training and the prediction, okay? So that's this part, not a lot of hard. And what next is we are going to apply what we just apply our learning algorithm, is it, to find the training result. Is it, this is a predicted value, is it? Then we are going to draw, okay, the three clusters. So this part is drawing of the three clusters. The first cluster is you want to add, because you remember the y values in the data that we generated are 0, 1, 2, is it? So we want to know, okay, if the data is 0, if it's all 0, so this applies what we learned in pandas. You can apply kind of filtering, is it? You apply this condition to filter your data. Okay, so if it is 0, then you get the corresponding x value, is it? And then you are going to draw it, is it, with a certain color, okay? So, and the last draw is to draw the centroid, is it? So with our training, is it, with our training, we can find the centroid x, y value, is it? So over here, so the k-means, if you call the k-means parameter cluster centers, you can find its center, okay? And in this case, it's identified by the star, okay? And then clearly you can see, oh, yeah, it cluster quite well in this case. Is it, for each cluster, it uses different color and shape to identify, and also shows the centroid. So in this case, we have three clusters. And looks like it works quite well, is it? And then next, let's see. Here, there is a concept previously we discussed. We call it inertial, is it? What is the inertial is, we said it's the sum of the square of arrow. We call it distortion, is it? A distortion. And then what over here, next part we are trying to do is, over here, we are going to use a loop, okay? We are going to loop 11 times, is it? And we are going to change the number of cluster, is it? 1 cluster or 2 clusters, 3 cluster, 4 cluster, 5 cluster, is it? And we are going to apply with k-means, okay? After that, we are going to have the inertia, is it? That parameter can be collected, is it, that coefficient? Okay, after you collect it, then you can draw this relationship, okay? And then let's see. And after we apply what we just get the data, the inertial, is it? And then you can find, is it, with the number of cluster increasing, your inertia is decreasing, is it? So that means the result is better because you want to minimize that sum of the error, is it? So over here, you can also clearly see, is it, when we have 3 cluster, and if you have more cluster, of course it improve, but there is no huge difference, is it? So this is a pretty a good cutoff point, is it? And if you also take a look at the shape, it looks like an elbow. As it looks like an elbow. That's why we call elbow approach, is it? So with the elbow approach, the elbow kind of plotting, then it can help you identify the optimal cluster numbers. Okay, so that's over here, the elbow concept. It's kind of over here that you find the elbow, okay? Okay, and then what next we discussed, you remember previously we discussed how do we choose the best number of cluster. Is it another way to do it? It's called silhouette plotting. Okay, and with silhouette plotting, there is a concept called silhouette coefficient S in this formula. So what it is, it's given the formula. Okay, within the formula, what is AO? AO is the average distance between O and other data point within the same cluster. And the B is what? B is minimum average distance from selected point to all clusters. Okay, to all other clusters. And previously, we also explained if this value close to 1, then that's a very good clustering. Is it? Of course. That means your B is far greater than A. Is it? And you will have B over B. Is it? That means all of your data within one cluster close to each other, but among different clusters, it's further away. So this is further away. Is it? But within your cluster, it's close. It's very close. Is it? So that's why with this silhouette coefficient, it clearly can reflect how good your clustering is doing. So that's the concept over here, the silhouette. Then how do we draw silhouette? Is it? So to draw silhouette, to get the silhouette coefficient, you need to also import from sklearn matrix, import silhouette samples, okay? And then over here, you apply the k-means. Here we have 3 clusters, so nothing new here, is it? And you have the prediction over here. We only have 3 clusters, the 3 cluster label, is it? And then the silhouette value, is it? Then you just call this silhouette sample method and then plug in your X values and the predicted values. And of course, you need to specify the distance you pick. Is it here is that I'm going to pick a Euclidean distance. And then you can start to draw, okay? And over here later on, we will see the draw basically is just a bar drawing. And then over here, we are going to have 3 clusters. So that's why we have a loop to draw for each cluster, is it? For each cluster, then you're going to get the silhouette values, is it? And based on your sample located fall in which cluster, is it? And you're also going to sort these values, okay? Sort the values. And this is, we're also going to define the lower bound and the upper bound of your range of the distribution. And in our example, basically, it's every 50 is 1 cluster. Is it? That's why we have 50 as a cluster, the silhouette. We're going to have 50 silhouette values, okay? Because in each cluster, we have 50 samples exactly fall within that cluster, okay? So over here, we are going to do a horizontal bar drawing, is it? And the bar value is going to be based on the silhouette values. And these silhouette values, there are 50. numbers. Okay, so basically it's a list of numbers. Okay, it's a series in this case. As a series, and the height of your bar is going to be 1 point, so it's unit 1, is it? But you have a range of the data for your lower bound and upper bound you're going to draw, okay? And so that's the general idea about this silhouette diagram, okay? And over here, I also output of the silhouette values, is it? And from this drawing, so this looks at the result of the silhouette values. Okay, the silhouette values over here, because you have 50 samples. Okay, that's why the value looks like it's not a pure bar, because generally speaking, bar is supposed to look like a rectangle, is it? And over here, it's not a rectangle because we have 50 samples and each of its silhouette values, is it between 0 to 1, is it? And from this silhouette drawing, you can see this cluster is quite good, is it? Because all these 3 silhouette diagram, this bar, the shape looks very similar, and the widths are the same, the height are the same, similar, is it? So that means this clustering is quite good, okay? And here it shows the bad clustering. The bad guy, in this case, with that data, we do 2 clustering, okay? And we change it to k-means plus plus, okay? For our clustering, and then in this case, you can see it's only 2 cluster, is it? With 2 cluster with the silhouette result, is it? This is very unbalanced, is it? Very unbalanced. This part is very wide, and also you can see the silhouette value is not close to 1, is it? In this cluster, is it? So that's why we said this is bad. Okay, so that's why we say silhouette can help a lot to the performance about about your clustering, okay? And next, let's see the hierarchical, okay, clustering. The hierarchical clustering here, we use different data set, okay? So this is our data set looks like, okay? It has 3 features, okay? X, Y, Z, and I have 5 row of the data, okay? 5 samples, so basically. We have 5 samples, but we have each sample has 3 features, is it? Okay, and like previously we explained, is it? For our hierarchical, we need the distance matrix, is it? So distance matrix, then we need to import the psyche. So the sine pi, okay, this is the sine pi package, okay. From that, you can import a spatial distance model, is it? And over there, you can import distribute and score form, okay. Those guys, use those, you can build the distance matrix, okay. So the distance matrix, like we explained, it explains the distance, is it? So over here, it shows distance between pair of samples, is it? And you can also specify the distance, is it? So this all shows the distance, okay? The pair, between pair of samples. And then what is the result will give us? Let's see, over here it says, we can also use our original input sample, okay, for our linkage calculation. So so over here, the very first case, it shows you use, the very first one, you use a square form, okay, the square form one. The square form one is not a good choice. Okay, so over here, the square form one is not going to be, so it's an incorrect approach if you use square form distance matrix, okay. And the second one, what it shows is you can condense the distance matrix, like over here, is it? And over here, you call the linkage, okay. The linkage, what it generate. So this linkage what it generates, you remember previously we discussed is, okay, so these two samples, is it, and you find the distance between these two samples are the shortest, is it, the closest, and then you group them together, is it? And then you may find, okay, after you group these two together, the next sample close to this cluster, is it? Then that's going to be the distance between this sample and this cluster, is it? So what this linkage, you can see, result gives you, is it? It gives you all of the cluster, is it? And also gives you the row label, is it? The row label is, okay, so it's between this one and this one. Okay, so it gives you what the two will be clustered together. So this row label basically represents from the intermediate definition number of the cluster. Okay, cluster. And with this linkage, what it generated this kind of output. And it also gives you the distance, is it? So between like the distance between this sample and this cluster, is it? Also give you the distance. Okay, and also it tells you a number of clusters, is it, items within the cluster. So that's what the linkage result gives you. And here it also shows the third approach. You can also use the sample, input the sample matrix, is it, the original values, is it, to generate the linkage, okay? And once you generate this linkage, like I already explained, is it, with the linkage, basically, then you can, from the linkage, so over here, this linkage output is called a raw cluster, is it? And with this raw cluster data, you have all of the information of the cluster, is it? Then you can start to do what? To draw your dendrogram, is it? So you can just call the SciPy cluster hierarchy, the dendrogram the dendrogram, that method to create the dendrogram diagram for us, okay? And what over here you're going, so be careful, this, you need to plug in what? You need to plug in with a linkage data. Okay, the linkage object, basically. You need to plug in. So previously you needed to call the linkage, okay? That's the idea here. And then based on that, we'll generate this kind of dendrogram. Okay, dendrogram. And with this dendrogram, then you can clearly say, okay, if I want the distance be 5, suppose. You said, okay, I'm going to use a threshold of 5 to cut. Then what you will see, you will have 1 cluster, is it? And you will have 2 clusters, you will have 3 clusters. And if you pick your cutoff distance as here, then you will only have 2 clusters, is it? So with this dendrogram, it's a very easy help us to draw to find out the clusters, okay? And the heat map, it's not very important to us here. And what the next shows us, you can then also call agglomerative clustering, is it? And with sklearn, okay, and you plug in and specify number of clusters and the linkage and the distance calculation, and then you can apply the fit predictor, and then you can predict which cluster it is it? Over here we have 3 clusters, is it? And if you just have 2 clusters, then your sample should go to which cluster, it clearly give you the idea, okay? And the last example shows us about the density one, okay? For the density one, this time we use a different data, use this 2 moon data, okay? Also from, it's famous from the sklearn data set, okay? And we also try to apply different clustering. We apply k-means, and we also apply what? The agglomerative clustering, is it? And you can clearly see from this two diagram, using k-means and using a gamma clustering give you the result. It's completely different. Is it completely different? Okay. And then if we take a look, the last, if we apply the density one, is it for the density one, then this gives you very good clustering, as it clearly identify the two cluster of the data. So over here, what we learned today is the clustering, is it? So clustering is unsupervised learning, and based on your data, you can try with different clustering approach that we discussed today. And basically, and that